the rate law is usually equal to some constant, some calibration constant. And there's more to K than just a calibration constant. But for now, let's just call it a calibration constant, times whatever the concentration is, raised to some power. And the good news is, when you solve these things, most of the reactions that you're going to run into for a given reagent, the power is going to be either 0, 1, or 2. Now, that's not the only thing it could be, but the vast majority of cases, it's just going to be K to the A to the 0 power, or the 1 power, or the 2 power. For example, if I had this reaction here, and I wanted to try and find the rate law for it, I have that data, again, the concentration, and then the initial rate as it jumps to the next concentration, as it jumps to the next time interval. Using that data, I should be able to determine the rate law for A. Do you see what's happening to A as I go from 0.1, as I change the concentration, as the initial concentration changes from 0.10 to 0.20? Do you see what happens to the rate? How the rate is? And it makes sense because these are 3 different experiments. In each of these experiments, I'm starting with a different concentration. I'm determining an initial rate. At 0.10, the initial rate is 0.015. Now there's a calibration constant, the K, that connects those 2 pieces. And the next piece is trying to find the power of it. Now, what happens when I doubled A?
The initial rate is also doubled?
Yeah. So that tells you something about the relationship between the rate and the concentration A. So if when I double A, I double the thing that it is equal to times K, what do you think the power of A is? Do you think it's 0, 1, or 2?
Would it be 1?
It is, because there is a linear relationship. So if I write that, equation, then when I look at my rate of reaction, and if I write it as the generic rate law, K, A to the n power, then if I double A, my rate doubles, which suggests that the power here is 1. Okay. So this is a trick that we use to find the rate law. I'm going to show you 3 different tricks, not all tonight. We'll probably just do this one tonight. But this trick will help you find the rate of reaction. This is called finding the rate by inspection. By basically looking at this data and asking what happens to the initial rate when I double the concentration or triple the concentration. And if the same factor affects the rate as whatever I did to the concentration, then that's a linear relationship, and the reaction has a power of 1, or the equation has a power of 1. It's a first order reaction. And they're not all going to be first order reactions. Like, for example, in this one, what do you think happens? What happens here when I double the concentration?
The initial rate doesn't change.
Right. So what's the power of A if I double A?
Would it be 0?
You got it. And 0 order reactions are fairly common. What it means is that the reaction is not actually dependent on the material being consumed. Reactions that go by a catalyst, sublimation processes, multi-phase reactions where they happen on an interface. The concentration of the stuff on the other side in the other phase doesn't matter, because it's really about the surface area that they can react on. So reactions can be first order. In other words, they change linearly. They can be zero order. The rate doesn't affect, the concentration doesn't affect the rate at all. They could also be something like this. What happens here when I doubled the concentration of A?
It's more than double.
It is more. So the concentration went up by 2. What did the rate go up by?
Another almost 0.045. So it's not.
So it went from 15 to 60. What's 60 divided by 15?
You said 60 divided by what?
By 15.
Oh, it's 4.
You got it. So do you see how the rate quadrupled?
Yeah.
Okay. So if instead of the rate, if I took the concentration and I doubled it and the rate quadrupled, what's the power of N now?
That's the second power, correct?
Yeah. And
Okay.
you can have those. In fact, the most common rate laws that you're going to run into, are either zero order in N or first order in N. In other words, the power of N is first order or second order. And the first trick that we're going to explore here is finding a reaction when it's zero order, first order, or second order, just by inspection. And these will be the most common ones. These are the ones you're going to run into the most frequently. And so this is where we're going to, this is what we're going to get into next. And the challenges that you will have in the lab or in the homework is we'll give you a reaction like this. By the way, there's a typo in this one. That initial rate at the end should be 0.032. That's actually a typo in the textbook. I got to fix that somehow. But they'll ask you what is the order of the reaction. And then they'll ask you what K is. And in this case, what do you think? Is this a zero order, first order, or second order reaction?
First order?
Yeah, that one's a first order, right? Because I doubled A, and then the rate, which is dependent on A, it also doubled. So 2x to the first power gives me, well, 2x, right? It's a first order reaction. So, so for this one, for example, I could find that the rate law, because it's a first order reaction, I could find that the rate law, the rate of reaction, is equal to K times A, well, to the first power. And I just kind of leave it like that. Now, now that I have the rate law, the next challenge is going to be, what is K? Okay, K is going to be important. How do you think you're going to find K once you figured out that this is a first order reaction?
Would it be see, that's where I get confused. I wouldn't even know what number to pick from, but it would be like the 0.15 divided by 0.008.
Totally. In other words, you would take this equation that you're building, that you're forming, and you'd say, okay, I now know this is 1. I'm confident of that. And I want a relationship because I want to be able to give it to my buddy so that he can put any concentration in and get the rate of reaction. So he also needs this constant here. And the way I would find that is I'd go to my experimental data. I already know this is 1. I plug in the concentration, plug in the rate, the initial rate at that concentration, and solve for K. You could use any one of those 3. In fact, you could use all 3 of them, do it 3 times, and then average it to find K. for the homework, it'll be pretty straightforward. You just use one data set and solve for K, which is basically just, like you said, your rate divided by A. Does that make sense?
Yeah, it does.
Okay. I'll give you a heads up here. The units of K are whatever fits. So you are, when we talk about concentration, concentration will almost always be molarity, moles per liter, okay? Or capital M, just molarity. When you're talking about K, the units will be whatever it fits to make the stuff on the right equal a rate of reaction. Rates of reaction will always be molarity per second. So in this case, where you've got a single reaction here, the units for A are going to be molarity. And over here, it's going to be molarity per second. So for a first order reaction, what is the units on K?
Molarity times seconds.
Close, almost. Because I've already got molarity here. Molarity times whatever the units on K are going to be molarity per second. So for a first order reaction, it's just going to be inverse seconds or hertz. So 1 over second. You can also write it as second to the minus 1. All right.
Okay.
How about if I've got a zero order reaction, where, for example, the rate of reaction is equal to K times A to the 0 power. A is still molarity, but I mean, it's going to go away. The reaction is just basically going to be equal to K. What will the units of K be in that case for a zero order reaction?
What you said, moles per second?
Close. Molarity per second. Molarity, a little different, but you're right. The units there will be, for a zero order, will be molarity per second. How about if I've got a second order reaction? Rate is equal to K times A, this time squared. And again, A is always going to be in molarity, and this is always going to be molarity per second. What will the units of K be in that case?
Just seconds?
Definitely the inverse seconds. But this is going to be squared.
Oh, so it's molarity per second.
I've got two molarities here. I want one in my rate, so I actually got to put the other molarity in the denominator. Make sense?
Yeah.
Okay. So here's a tip. If you know the units of K, you know the order of the reaction. So frequently, when they're doing this homework or they're doing a test or they're doing a placement exam, they will give you K and they will write the units in it. And that's a subtle way of telling you if it's a zero order, a first order, a second order reaction. If it's inverse seconds, it's a first order reaction. If it's molarity per second, it's a zero order reaction. And if it's 1 over molarity per second, molarity seconds, then it's a second order reaction. So the units of K are a giveaway for the order of the reaction. That's another trick that you can make use of. All right. Now, we're just getting started with this because, for example, I've been showing you how to solve by inspection reactions where you have one reactant going to one product. Okay. On Friday, if you come back, we will talk about how we can solve something that looks, well, like this, when we have two reactants reacting with each other and producing C. Now, I'll give you a hint. It's not that much more challenging. It's just going to involve doing the same thing. Well, we got to set it up, but then we're going to do the same thing twice.